Good afternoon, everybody. Thank you for coming. Okay. Good afternoon, everybody. Thank you for coming here. Since this is a talk about reflection, I will, of course, start by talking about command line option parsing. I'm sure everyone loves code like this. Our application has 4 possible command line options. We iterate through all the arguments, looking for each possible option and processing it. This is tedious and error-prone. If we change any of the options, code needs to be updated in multiple places. And this code here doesn't do any error checking. If we add just the basic error checking, enough to avoid a crash if the user types in garbage, it becomes even more tedious. But what if we could ditch all of this repetitive boilerplate? Just define a struct that holds the values of the options and have the code automatically fill in the values of the struct from the command line arguments. That's it. No writing out the code for individual options, no code for parsing individual options. Just some generic code that does it all as if by magic. That's what reflection can do for you. Keep this example in mind as we go through the presentation. I'll show you the magic behind the parse options function later on. Welcome to my presentation about C++ reflection, where I'll explain what reflection is, go over the proposal that is working its way through the standards committee, and give some examples of how reflection can be useful. I am David Olsen, the lead engineer on the HPC C++ compiler team at NVIDIA, where I keep our compiler, NVC++, running smoothly on many of the biggest supercomputers in the world. I was the driving force behind the NVC++ feature of running standard parallel algorithms on GPUs. And I am supporting NVIDIA's efforts to run upcoming standard features, such as linear algebra and P2300 senders, on GPUs. Before I overwhelm you all with code examples and proposal details, I should spend some time reflecting on what reflection is. Reflection comes in 2 parts, introspection and injection. We will cover introspection first. This is probably what comes to mind when you think of the word reflection in a programming context. Reflection is when a program looks at itself and observes its structure and how it is put together. In other words, the program can ask questions about itself, such as, what kind of type is this? Or what are the public data members of this class? Or where are the buffer overflow bugs in my code? Just kidding about the last one. The program looking at itself is an important part of the definition. A program asking questions about another program is a static analysis tool, not reflection. Given that it's known as reflection, you would think that a mirror is a good analogy. But no, a mirror only shows the surface of what it is reflecting. A better analogy, in my opinion, is an X-ray. An X-ray lets you see not just the surface, but the interior structure. Reflection lets a program look at how it is put together, not just at its external behavior. When asking questions about itself, the program works with reflection values, usually referred to as reflections. To get a reflection value that can be queried, there has to be some way to get from the world of code into the world of reflection. This is known as the reflection operator. In the X-ray example, the reflection operator is the X-ray machine. That is what converts a real-world object, in this case your leg, into a reflection value, namely the view of the bones inside your leg. The other side of reflection is code injection, also known as reflective metaprogramming. This is the opposite of introspection. This is lumped together under the general term reflection and differs from other kinds of metaprogramming because the results of reflection queries are used to generate code. I looked for a picture of a robot fixing itself to represent reflective metaprogramming, but I couldn't find a good one. So you'll have to settle for Escher's drawing of 2 hands drawing themselves. While introspection needs to have a reflection operator to go from the code world to the reflection world, code injection needs to do the opposite, going from the reflection world back to the code world. Every decent reflection scheme will have some way of doing this, though it is usually not as simple as an operator. For reflection to be useful, There needs to be something unknown for the program to ask questions about. The unknown thing could be anything, but it is usually a type, or reflection queries usually start with an unknown type before moving on to other kinds of unknown things. It is important that the program doesn't know what the type is, but that the compiler does know. If the code knows what the type is, there's not much point in asking questions about it. If the compiler doesn't know what the type is, then asking questions about the type won't result in useful answers. If you have code that is working with unknown types, you usually have polymorphism of some sort. It could be compile-time polymorphism, such as C++ templates. Or it could be runtime polymorphism, such as object-oriented programming and class hierarchies. Programming languages that don't have any polymorphism, such as C, don't have reflection, because there are no significant amounts of generic code operating on unknown types. An example of code using an unknown type at compile time is a C++ template. In the function template here, at the end, the code inside the function doesn't know what the type t is, but the compiler knows what t is when the function is instantiated. You might point out that the code that calls the function probably knows what t is, but the code inside the function does not, which is the important thing. Code works with a type that is unknown at runtime in dynamically typed languages or in languages that support object-oriented programming, especially in languages such as Java that have a universal base class. Compile time reflection does introspection on static types, and code injection causes different code to be generated by the compiler. It is a good match for statically typed languages with static polymorphism or generics, as it is referred to in most languages. Runtime reflection does introspection on the dynamic types of objects. It doesn't affect the code that the compiler generates, but instead causes different code to be executed at runtime based on the dynamic types of objects. It's a particularly good match for object-oriented languages with universal base classes. Spoiler alert, C++ will have compile time reflection. To help you understand how C++ reflection fits into the bigger picture, I want to quickly go over some other implementations of reflection. Let's look at how reflection is done in C#. While I spent 1.5 years programming mostly in C#, that was some years ago. My C# skills are quite rusty. There are probably some mistakes in the following slides, but I think the concepts are correct. C# reflection is runtime only. It predates C# generics, so it is designed to work with C#'s universal base class model. The reflection operator is the getType method that every object has. It returns a reflection value of type that reflects the dynamic runtime type of the object. Once you have the reflection of the class type, you can navigate around with each kind of thing represented by a reflection value of a different type, such as method info, constructor info, or field info. Code injection in C# is also done at runtime. You can create a new object by calling the createInstance method of reflection class activator. You can call a member function that was found via reflection by calling the invoke method of the reflection class method info. I will use this problem as my basic reflection example several times in the talk, so let me go over the problem statement in detail now. Assume that we have been sloppy in our API design, and we've created some containers with a size method and some with a length method. And we are too lazy to fix up all the containers and make the APIs consistent. So we want to write a function that accepts any kind of object, checks if it has a method named size or length, call that method, and return the result. This is slideware, meant to show the use of reflection, so the error handling is minimal. This is the C# solution to the problem. We have a method named size or length that takes a single parameter of the universal base class object. First, we use the reflection operator, the getType method, to switch from the code to the reflection world. Remember that getType returns the reflection of the dynamic type of the given object, not a reflection of class object. Once we have a reflection of the class type, we get that class's methods and iterate over them, looking for one named either size or length. If we find one with the right name, we call that method using C#'s code injection operator of method.invoke. Method.invoke returns an object, so we have to convert that to an int before returning it to the caller. And we're done. C# has code injection capabilities beyond the simple ones in the previous example. It is possible to create entirely new classes and functions at runtime. It is not easy to do. Creating function bodies requires emitting .NET bytecode, which makes the programmer do the work that compilers normally do. Here is a very simple example taken from a C# reflection tutorial. The highlighted code is emitting .NET bytecode for the function bodies. If we wrote the code directly, rather than using reflection, this is what we would have. Most of the code was implementing these two simple functions at runtime. Now let's look at how C++ currently implements reflection. Hint, not really. That's why there is a proposal, which we will get to eventually, that does reflection properly. There's a tiny bit of runtime reflection in C++ right now, emphasis on tiny. The type ID operator can get a std type info object representing a type, even for the dynamic type of an object in some cases. While this runtime type information is very useful to the compiler, behind the scenes it is used for exception handling and dynamic cast. It is essentially useless to the end user. The only thing user code can do with the type info is to get the name of the type, which might be a mangled internal name, not the user visible name. I don't know of any plans or desires to expand the functionality of type ID or type info. It is a dead end in the quest for C++ reflection. Type traits are much more useful. They allow for compile time introspection of types. There are lots of standard type traits. These are all the ones I could find. But type traits only work on types and on the properties that can be represented in the type system. You can't get the members of something or even the parent scope of a name. You can't ask questions about functions except for things that are in the function's type or that affect template argument deduction. While type traits are extremely useful and were a great addition to the language in C++11, they are lousy at implementing reflection because they were never intended to be the reflection solution. Type traits and many other parts of template metaprogramming are an outgrowth of the magic of function template argument deduction that happens during overload resolution. These rules can also be used to resolve class template partial specializations, which is what type traits are built on. One last thing in current C++ that is not reflection, but that is reflection adjacent, requires expressions. A requires expression makes it very easy to ask whether or not a chunk of code is semantically valid. Requires expressions can do a couple other things, but their primary purpose is to check for code validity. It was possible to do this before with template metaprogramming, but requires expressions make it so much easier. While you can view this as a kind of introspection of the code, it's more of a surface view like a mirror, not a look inside like an X-ray. While requires expressions are not reflection, they can be used to solve our size or length problem, though the solution is not ideal. Again, we have a function named size or length that takes an argument of any type, but this time the type of the parameter is a template parameter rather than a universal base class. Rather than iterating through all the member functions of TE, instead we check if calling the size member function with no arguments is valid code that returns an integral type. If it is valid, then we call it and return its result. Then we do the same for length. Because we don't have true reflection with code injection available, we can't just call whatever member function happens to meet whatever criteria we are looking for. We have to check each possible member function one at a time and call that member function directly. This scheme would break down entirely if we were looking for member functions whose name fits a certain pattern, or if we were looking for member functions with certain properties other than its name. One last stop on reflection survey, a proposal for standardizing reflection in C++ that was ultimately dropped. In the 2010s, there was a lot of work to get reflection into C++ using a compile-time template metaprogramming approach. A reflection value was a nameless, unique type. To figure out what kind of reflection a type represented, you would check if the type satisfied one or more of a large number of concepts. The reflection operator was the keyword reflexper. Reflection queries were done via type-based template metafunctions. Because everything was type-based, reflection programming was done via type alias declarations, as seen here. Getting from the reflection world back to the code world was done with more template metafunctions. To get the type from the reflection of that type, use getReflectedType. If the reflection value represented a function, member function, variable with static storage duration, or a non-static data member, then getPointer could be used to get a compile time pointer to the thing. The reflection effort made it as far as being published in a TS, or technical specification. But the TS was never merged into the C++ standard. In the late teens, the standard committee decided that template metaprogramming is just too cumbersome, and the context per functions made for a better API for reflection. So everyone shifted their efforts to other reflection proposals. A Clang fork that implements the reflection TS is still available on Compiler Explorer, so I can give you a taste of what working reflection TS code looked like. We have a function named size or length that takes an object of any type. We transfer into the reflection world with the reflexper keyword. Then get the reflection of the entire set of public member functions of the class. They are represented as a type, which is why they are stored as a type alias. Because we are working with type lists, we need a recursive class template with a partial specialization in order to iterate over the types that reflect the member functions. The unpack sequence template metafunction passes the type list to our class template. Our class template checks if the current member function is named size or length. If so, use getPointer to get a pointer to the member function, and use the pointer to member function call syntax to call that member function on the given object. From the complexity and verbosity of this code, you can understand why there was some pushback against the reflection TS and a desire for something better. That something better is reflection for C++ 26, which is currently making its way through the standards committee, where it is known by its paper number P2996. This is the meat of the talk. This is the part you should pay attention to if you are interested in C++ reflection. All the background I have given wasn't strictly necessary, but hopefully it gives you a foundation to better understand P2996. Some past reflection proposals have suffered from being too big. The committee wasn't confident that they could get all the details correct on the first go. And once a bad feature is in a release standard, it can be very hard to fix it. So the authors of the current proposal have taken the approach of going for a minimum viable proposal. They hope that the proposal is the right size, big enough to be really useful, small enough that they can get it right, and open to extensions that will fill out the reflection functionality at a later time. The minimal viable proposal is one where introspection is nearly complete, but code injection support is minimal. Focusing on introspection first makes sense for two reasons. First, the complications of code injection are harder to solve than the complications of introspection. Second, code injection without introspection is mostly useless, but introspection without code injection is very useful. This proposal is entirely compile time. This must be distinctly understood, or you will get nothing out of what I'm about to explain to you. P2996 is making its way through the standards committee on both the language and library tracks. The language part of the proposal has been design approved, and the core wording group is starting to look at it. The library part is currently going through design review and library evolution. If none of that made sense because you are unfamiliar with the inner workings of the C++ standards committee, don't worry. TLDR, the reflection is on track to make it into C++26. It's not certain, but there is still lots of work to do, but the chances are quite good. On to the actual contents of the proposal. All reflection values have the type std meta info. Different reflection values are different compile time values of meta info, not different types. Meta info is an opaque scalar type that is only useful at compile time. All functions that work with meta info objects are const eval, which means they are compile time only. Why one type for all reflection values rather than different types for different kinds of things? Like in C#, 2 reasons. First, the C++ language has changed in the past and it will continue to change in the future. Reflection needs to represent the structure of the core language. Reacting to language changes will be easier if the structure of the language is not encoded in the type system. Second, and I think more importantly, it is easier to represent a heterogeneous container or a collection of mixed things. A list of template arguments can be stored in a vector of info, even if those template arguments are a mix of type template arguments, non-type template arguments, and template arguments. The reflection operator, which is how you transition from the code world to the reflection world, is a prefix unary caret. The operand can be a type or the global namespace or almost anything with a name. The result of the caret operator is always a compile time value of type std meta info and is the reflection of the operand. So some examples of this. If we do caret int, that's a reflection of the built-in type int. Caret std vector int. Sorry. It's a reflection of the type std vector int, std allocator int. Remember, vector has a default template parameter, and that's recorded in the reflection of this type. If we just do caret std vector, that's a reflection of the template class, or of the class template std vector, not of any particular instantiation. Those are separate. The reflections of the types that are in the instantiations and the reflection of the template itself are separate, are different things. If we take the reflection of std string, that's a reflection of the alias std string. Remember, std string is a type alias for basic string with a bunch of arguments. So alias is, in the core language, an alias and the type that it aliases are identical. There's no way to distinguish them. But in reflection, they are separate. You can get a reflection of the alias itself, and then you can convert that into its underlying type. This is a reflection of the global namespace. This is the reflection of the namespace std chrono. And this is the reflection of the function std fopen. So, to go from the reflection world to the code world, use a splicer, which is a pair of brackets made up of square brackets and colons. The operand inside the brackets must be a compile time expression that is, or that can be implicitly converted to, std meta info. Splicers are hard to describe and are best understood with examples. Here we get the reflection of the built-in type int and store it in the const expr variable r. Then we splice the reflection variable named r back into the code world. Because r is the reflection of int, the variable x has type int. It is possible to get the reflection of something and immediately splice it back into the code. It's legal, but not particularly useful.
The thing on the right-hand side of the caret, does that have to be a name? The thing on the right-hand side of the caret, does that have to be a name declared in the text? Or can I say something like caret decal type of some expression?
You can, if it's a type, it can be any type, even nameless one. So caret of decal type of some expression, that will work. And that'll give you a reflection of the type.
Thank you.
But you can't do, the thing on the right cannot be an arbitrary expression. If it's something without a name, it pretty much has to be a type. You may have noticed the use of type name before each of the splices. The keywords type name and template are sometimes required before a splice operation, similar to how type name and template are required before names that depend on a template parameter. In all these cases, the keywords help the compiler with its syntax parsing. In the example with the template keywords in this slide, the compiler needs to know that the splice of VT is a template, so it knows how to correctly parse the less than character just after the splice. A splice can be used almost anywhere the reflected thing is valid. So if we take the reflection of the type long, we can splice that back in almost anywhere that a type can be used. So as the template argument for vector, as the type of a variable, or as the type inside a static cast. Notice that in the static cast, we don't need to use the word type name because the only thing that can be inside the brackets of a static cast is a type. The compiler already knows that that has to be a type. But type name is required in the two other places. If we take the reflection of a namespace, we can splice that in the qualifier part of a qualified name. So this is sort of a backdoor way to give you a namespace variable, though at compile time, not at runtime. We take the reflection of a function. We can use that, we can splice that in and use that anywhere that the function can be used. So taking the address of the function or calling the function. And the splice of a data member within a class. Or sorry, we take the reflection of Z within A, and we can splice that back wherever, so on the right side of a dot for an object of type A. But note that the reflection is of the data member Z within A only. It's not any data member named Z. So if we have two classes, each with a data member named Z, when we take the reflection of Z within class A, we cannot splice that into a member expression of an object of type B. The compiler will report an error as shown here.
I noticed that you're always putting context for every time you declare a thing. If you don't put context for there, is it invalid? Is it invalid to have a non-context for meta info?
In many cases, I think if meta info are compile time only, so you should always be able to make them const expr. If you're in sort of a const expr context like a const eval function, you can probably leave it out, but I'm not sure. I've always put it in since it never hurts to put the const expr in there.
Okay, got it.
And you can never change, once you create a variable of type meta info, you can never change it. They're non-mutable variables, even in the compile, even in a const expr context. So up next, we'll discuss the meta functions in the proposal. They are all const eval functions in the std meta namespace. The parameters are generally reflection values of type std meta info. The return type is appropriate for whatever was asked, which is often a Boolean, a meta info, or a vector of meta info. I won't go into, so this relies on std_vector being const_expr, which is a recent change to the standard finally. But it depends on, yeah, strings and vectors being compile time classes, being able to use them at compile time. I won't go over all of the meta functions because there are too many, but I will cover different groups of meta functions so you can get a good sense of what they can do. And note that almost none of these are template functions. These are regular functions that happen to be const_eval. There's no templates involved here in most cases. So these are the meta functions that you can use to ask, what kind of thing is this a reflection of? So you can see we can have reflections of namespaces, functions, variables, types, aliases, templates, concepts, class members, base classes, and a bunch of other things, or a few other things I didn't list here. But this is, if you have a reflection, you can start with these to see what kind of reflection is this.
So I guess the fact that it's just one type means that there's no overloading possible. So I assume that maybe using like requires clauses with these functions can help with that. If I want the same named function to work differently on different meta info objects.
Right. As you pointed out, you cannot overload a function based on what your reflection represents. But I hadn't thought about it, but yes, you could possibly throw a requires clause on your function to weed that out. Since these have to be evaluated at compile time, they are suitable for use in requires clauses. We'll see. Okay, things dealing with names. You can get the name of something if it can have a name. The name of is the simple name. Display name of gets you a more useful name, though display name of is implementation defined exactly how it's represented, the more complex things. You can ask for the source location of where the thing that you're reflecting was declared or defined. All the queries that you can do with type traits, you can do them with these meta functions using reflections of the types. They have the same names except that the word type is at the beginning. With type traits, you already know that the thing you're asking about is a type because that's the only thing it works on. With the meta functions and reflections, the reflection can represent anything. So if you want to ask something specifically about a type, you need to distinguish that in the name. Otherwise, there would be conflicts like for is function and is enum and some of the other functions. So everything you can do with type traits, you can do with reflection. But with reflection, you can ask about things that you can't get through type traits, like the accessibility, public, protected, private. There's also some queries to say, is this thing accessible from this location or from this context? You can ask about linkage, internal linkage, external linkage, the virtualness of a function, and other things, other minor things. Is it defaulted? Is it deleted? Is this constructor explicit? Those are all, that information is all available through reflection. And then getting the members of something, another new thing. There was no way to do this before. So all the members of functions return vector of info because you can have it's a collection. So members of can be applied to a class or a namespace. The next four are only applicable to classes. And then the last one, the enumerators of, is you can only apply to enumerations, to enum types. These do not look at accessibility. They will return all the appropriate members, whether they're public, private, or protected. If you care about accessibility, which some people really do, and that's very important, you can use the accessible version of these same functions. They behave the same, except they take an extra parameter, which is a reflection of the context from where you want to check the accessibility from. And so this will give you just the members So these are only apply to classes, and they'll give you just the members that are accessible from the context that you have provided. And what I find very interesting and useful is the one about templates and template instantiations, template specializations, the meta functions for this. So you can ask, is something a template specialization by calling has template arguments. Turns a bool. It can be a specialization of a class, of a function template, of a concept, of a variable template, just as anything. Does it have template arguments of any sort? Or a specialization of an alias. Remember, type aliases can be templated. So you can ask, is this a specialization of an alias? And then, right, if it does have template arguments, you can get what those template arguments are. It'll return a vector of the reflections of the arguments. And you can also get the base template, a reflection of the base template. So if we had a reflection of vector int, we call template of, it'll give us a reflection of the vector template itself, the base template. And calling template arguments of, it'll give us int and stood allocator int, because those are the template arguments of the specialization vector of int. So I mentioned you can't use the reflection operator on an arbitrary expression, but you can have reflections of values, of compile time values. So to get the reflection of the value, you have to use the reflect value meta function rather than the reflection operator. So you give reflect value any compile time value, and it'll give you back the reflection for that. And if you want to go the other way, use extract, and you have to specify the type that you're expecting to get out. And you give it a reflection of a value, not of something else. It has to be of a value. And it will give you back the compile time value that is being reflected. There's also related to that reflect object and reflect function related to reflect value, but subtles are different. The subtleties are different. They're different, and I don't have time to explain those here. So error reporting. What if you give it a nonsensical query? So say you ask, is the type int a pure virtual function? It doesn't make sense. The type is not a function. So, but for the Boolean queries that return true or false, if it's nonsensical, the query just returns false. So yes, the type int is not a pure virtual function because it's not a function. But for other queries, it results in a compiler error. So if you ask for the offset of the type int, offset of expects a data member, a reflection of a data member. The offset of int doesn't make sense, and there's not a false. You can't just return false. So it's a compiler error by saying, right, offset of int is not a compile time expression, and you're in a compile time context, so it's an error because of that. And the compiler also includes in that error this note saying exactly what happened. It was expecting a reflection of a non-static data member, but it got the reflection of a type. So this note is unfortunately buried a bunch of other notes because the compiler is not good at knowing exactly what information of the context is most useful. But it's there if you know to look for it, telling you exactly what you did wrong. There are some more features of the reflection puzzle still to be covered, but we have covered enough that it is time for some real examples. But before doing that, we need to take a short detour. For compile time to reflection to be really useful, there must be a way to loop over a collection at compile time. And no, a regular for loop inside a constexpr function isn't good enough. There's a standards proposal to add constexpr loops to the language, referring to them as expansion statements. That proposal stalled for a while, but is moving through the committee once again. Even though expansion statements aren't in the standard yet, it is so useful to reflection that P2996 and the slides in this presentation are written assuming that expansion statements exist. When you see what looks like a range-based for loop with template in front of it, Read that as a loop that is expanded and unrolled at compile time. Most compilers don't implement expansion statements yet, so a workaround is available. The syntax is rather ugly, but the effect is similar. The template for syntax will be used on these slides, but the expand syntax will be used in all the compiler explorer links that are in the lower right-hand corner of all the slides, so that the code will actually compile. One final look at our size length problem. If the argument is of a class type, get the methods of that type. Get the members of that type, and iterate over them. If the member is a function, named size or length, that can be called with no arguments and it returns an integer, then call that member function. Note how reflection and requires expressions play nicely together here. Reflection makes it easy to look through all the member functions, searching for ones that fit whatever criteria we are looking for, but it's much easier to use required expressions to validate that whatever is found can be used in the way that we want to use it. Now back to the very beginning of this talk, where I hopefully piqued your interest with this magical parse options function. This is how the magic works. The type that holds all the configuration options is specified as an explicit template argument, template parameter. Iterate over all the static data members of that class. Search through all the command line arguments, looking for one that matches the name of the static data member with a double dash in front. If the parameter is of type bool, that's easy to process. Otherwise, we use I/O streams to parse the value of that argument. Throw in a little bit of error checking, and we have a decent generic command line parser. There are a few functions in P2996 that are worth calling out because they are not like the others. Splicers behave as if they insert the thing being reflected directly into the source code, and then the compiler compiles the code as if the thing being reflected had always been there. But the functions substitute and define class change the state of the compiler without injecting any code that is compiled. The function substitute performs a template substitution. The inputs are the reflection of a template and a span of the reflections of all the template arguments. And the output is the reflection of the type that was created. The substitute function combines the template and the template arguments into a type, kind of like the line at the bottom, except that you can't do it that way because args is not a pack that can be expanded. The example of using substitute attempts to automatically propagate an allocator from the container to the elements owned by the container. If a container has a non-default allocator and the value type of the container is allocator aware, we can automatically change the value type to use the custom allocator. I don't know if this is actually a good idea, but until now it hasn't been possible, so we couldn't explore the issue. Reflection now makes this possible, so we can now figure out if automatic allocator propagation would be useful in some situations. This is how we can change the allocator of an allocator-aware type. If the given allocator is the default system allocator, or if the value type doesn't have any template arguments, then there's nothing to do and we bail out early. If the arguments pass those checks, then iterate over the template arguments of the value type that was given to the container. If the template argument is a specialization of std allocator, replace it with a specialization of the desired allocator. The allocator traits rebind is necessary because the template arguments for the two instances of the allocator are different. Once the necessary adjustments to the template arguments have been made, the new value type is created by calling substitute. And this is how change allocator would be used. In the definition of the container, we set the value type to the result of calling change allocator. If the value type is not a template specialization, or if none of the template arguments of the value type look like an allocator, then change allocator doesn't do anything. The value type of the container is the value type that was specified. But if the value type has an allocator as the template argument, then change allocator may change the allocator. Note that std vector has a default template parameter for an allocator. So when we say vector event, the compiler sees vector event with allocator event. In this case, change allocator returns a different type, a vector event with custom alloc event. While substitute will...
Sorry. If we have substitution, what happens if we have substitution failure? And is it an error or is it not an error?
It is an error. It is a compile time error.
So it's a hard error. We can't detect whether it will happen or not.
There is a function. There's a function, I think it's called can substitute, that you can do to check before you actually call substitute.
Excellent. Thank you.
I just read that an hour ago, so. While substitute will create template substitutions out of the reflection values, define class will, as its name implies, define a class using only reflection values. It doesn't create the class entirely out of thin air. One of the inputs is the reflection of an incomplete class, which must have already been declared. For now, only non-static data members are supported because they have the best combination of being both useful and easy to implement. Other kinds of members will come along later. The data members that define class should create are specified with the reflection of the type of the data member and struct containing other settings. Only the type is required. Everything else, including the name, is optional. The function data member spec is used to create the reflection of the data member that define class needs. Here is a very simple example. The code at the top behaves the same as the code at the bottom. Note that calling define class with a template specialization that hasn't been fully instantiated yet behaves the same as an explicit specialization of the class template. Here's an example that can be very useful for developers in the high performance space. Even though an array of structs is more readable and more maintainable, a struct of arrays often has better performance due to increased vectorization and caching effects. In many applications, data structures will be manually changed to use struct of arrays. Well, now with reflection, that change doesn't have to be done manually. Given any struct whose data members are scalar types, a new struct with corresponding members that are arrays instead of scalars can be automatically created. To do that, iterate over the data members of the given type. Create a new data member that has the same type as the old data member, but whose type is a std array, whose name is the same, but whose type is a std array of the old type and the desired size. Use define class to define a new type with the new data members. The implementation may look a little complicated, but the use of this is simple. And that's one of the goals of software engineering, to make things easy for the end user. It would be even nicer and easier if the use of the struct of arrays class came with member functions that make it look like an array of structs. But that will have to wait until define class can define more member functions and not just data members. Though people are actively working on that. I've seen some very promising approaches on defining a complete struct of arrays class with all the useful member functions. You may be saying this all looks good, but even if this makes it into C+26, it'll be at least several years before I can try it out. Wrong. There are already 3 implementations available on Compiler Explorer. EDG, who licenses C++ front end that is used in several compilers and in many static analyzers, was the first to come up with an implementation of this. It's a hidden option in the EDG front end, but a version of EDG which automatically sets that option is available on Compiler Explorer. select the EDG experimental reflection compiler. A fork of Clang, written by people at Bloomberg, I think, is available on Compiler Explorer. It implements almost the same thing. The two behave very similar. So select Clang experimental P2996. And then the NVIDIA HPC C++ compiler, NVC++, which is what I work on. It has an EDG front end. So we have actually made reflection available in our compiler. Because it's a production compiler, you need to specify the hidden option, which is reflection, to turn it on. But our compiler is available on Compiler Explorer. You've got to specify those options there. But also, it's available for download. The production one that you can download has reflection in it. So if you have a larger application and you want to try out reflection in a small part of it, see how it works, something too big to put on Compiler Explorer, you can download NVC++ on Linux and try it out. Running out of time. No, we're going to. Serialization is hard because no one has figured out how to automatically handle classes. The user needs to write a function to say how to handle classes. But with reflection, it's easy. Give a class, you iterate over the base classes, serialize each of the base classes. Iterate over the data members, serialize each of the data members. When I started working on this, I thought there would be a lot more. I was very pleasantly surprised about how easy it is. Deserialization is similar, but bit fields throw a wrinkle in this because you can't take an L value to a bit field. So you got to do extra code to deserialize into a regular variable and then assign it to the bit field. But it's quite doable. So reflection can serialize many classes automatically, but not all. There's still problems when lost the screen. OK. When the data members are references or unions, because it doesn't know which member of the union is active, or non-assignable. So the summary is a good serialization framework must still allow you to specify classes, specify how to serialize a class manually, but it can handle more things automatically through reflection. Future directions. A whole bunch of papers are being written that that are following on the P2996. Most interesting one is token sequences. Token sequence is what its name implies, a sequence of arbitrary C++ tokens. The tokens in a sequence don't have to be syntactically or semantically valid. They just have to be tokens. To be of any use, in the end, you need the tokens that are both semantically and syntactically valid. But the intermediate token sequences don't need to be meaningful by themselves. To create a token sequence, apply the caret reflection operator to a curly brace enclosed sequence of tokens. The curly braces need to be balanced, as the last example shows. But other than that, they don't have to be meaningful. Other tokens that are normally balanced, like parentheses, don't have to be balanced in a token sequence. The type of a token sequence is std meta info, like everything else reflection related. The proposal for token sequences is still in the early stages in its journey through the standards committee. The authors are hopeful that it can make it into C++26, but that is less certain for the main reflection proposal. And the token sequences have been implemented by EDG on Compiler Explorer. So you can try them out, and the Compiler Explorer links on these slides will work. Token sequences very much depend on const eval blocks, which are another proposal that is working its way through, not directly related to reflection, but useful for that. A const eval block can be used anywhere a static assert is allowed, and it encloses statements, and the compiler will run those statements at compile time. Without reflection, that's not very useful because the statements can't have any side effects, can't do anything useful. But with reflection, both with our substitute and define class, and with the token sequences, the statements can have side effects. So you need a place to run them at a well-defined time. So that's what const eval blocks are for. Token sequences are only useful if we can inject them back into the code. So the compiler will parse and compile them. This is done with the functions qinjection and namespace inject. Qinjection injects the given token sequence into the code at the end of the const eval block in which the qinjection call appears. Namespace inject immediately injects the given token sequence into the given namespace. Immediate injection is only available into namespaces because namespaces are the only thing that are always open to extension. For everything else, you can only inject into the currently active scope. Like most abstract ideas, this benefits from examples. We define two token sequences. One is the tokens necessary to define a context or variable named x. The other is a static assert that verifies the value of x. Then we inject both of these token sequences into the code. Because qinjection delays the injection to the end of the const eval block and namespace inject happens immediately, the variable x is defined before the static assert is parsed. Creating and injecting token sequences that consist entirely of fixed tokens is not useful. To accomplish anything, there needs to be a way for token streams to contain variables or placeholders of some sort that are filled in when the token sequence is injected. There are three ways to do that in the proposal. A backslash followed by a compile time expression in parentheses is replaced by a pseudo-literal token that represents the value of the expression. Backslash ID with a string-like thing or a sequence of those is replaced by an identifier token. That's the concatenation of the strings. Backslash tokens can be used to insert one token sequence into another token sequence. Okay, our example from a couple slides back. Let's parameterize those token sequences. So we can define any variable with any name of any type with any initial value in any namespace. The define function takes the name of the variable as a string and its initial value. It returns a token sequence defining the variable, containing the type of the initial value, the name of the variable as an identifier rather than a string, and the initial value. The check function takes the reflection of a namespace, the name of the variable as a string, and its expected value. It returns a token sequence with a static assert with all the right things in all the right places. We can pass the token sequences returned by these functions to namespace inject and qinjection respectively, and it produces code that defines the variable and asserts that it has the correct value. Notice how the backslash expression and the slice operator can be combined to inject a reflection into the code that comes from a token sequence. Another quick example of token sequences. This is roughly how enable if is currently implemented. But this can be confusing to those unfamiliar with template metaprogramming. The name enable if implies that there should be an if in there somewhere, but there is none to be seen. With token sequences are used instead, the implementation of enable if is much more clear. There's a very obvious if statement, and it's easy to figure out that type is defined when the condition is true and not defined when the condition is false. So tuple is a very useful class, but it is annoyingly hard to implement, as Bryce well knows. In particular, it is really hard to define the data members of a tuple because there is no good way in C++ to turn a list of types into a sequence of declarations. Existing tuple implementations rely on recursive template base classes to do that. But with token sequences, defining the data members of a tuple is almost trivial. Iterate over the type list within a const eval block, creating a token sequence defining a data member with a manufactured name and the correct type. That's it. Defining all the member functions and free functions for std tuple is left as an exercise for the reader. And skip this one. You can define properties. So the code on the left expands to the code on the right. Or equivalent to the code on the right. One last thought on future directions for reflection. If you really want to see the future of reflection and get a glimpse of where it might be headed, go back in time 7 years and watch Herb Sutter's CppCon keynote about metaclasses. The details have changed a lot since then, but the idea of taking code injection to the extreme is still worth considering and pursuing. Other resources. If you like talks, you can watch Inbal Levy's keynote from ACCU this year, Welcome to the Metaverse, or Saksham Sharma's talk from C++ Now, Reflection is Good for Code Health. Those are good talks about reflection. Saksham has some good examples, some things that I haven't tried yet, good uses of reflection. And if you really want, you can watch C++ Reflection Back on Track from C++ Now by me. But if you're here in this room or you're watching this online, there's no reason to watch that one. This one is more up to date. I don't know of any other reflection talks at this conference, but I know there are at least 2 scheduled for CppCon in September. In other words, if you are familiar with how the Standards Committee works and like seeing how the sausage gets made, here's a list of papers related to reflection that you might find interesting. But if large, inefficient, contentious committees are not your thing, that's perfectly fine. You are safe to ignore these. So, what I hope you will take away from this presentation. C++ reflection is coming. There is a very good chance that it will be in C++ 26, but even if it misses that, it will be in the standard before too long. C++ reflection happens at compile time. If you want to use reflection, you should up your compile time programming game. But you don't need to master template metaprogramming, since reflection is based on non-template const eval functions. So you do want to up your game on const expert functions and how to use those. C++ reflection is best at reducing the amount of boilerplate code, making it possible to do generically what currently has to be done manually. There is still lots of work to do. If you're interested in reflection, please try it out. Connect with others who are interested in reflection. Give your opinions and suggestions, and pitch in however you can be most useful. Thank you. So we're over time, so no questions from the audience, but I will stick around for anybody who wants to discuss things. Thank you.